And we'll move into the different variation models. Basically, we'll have three different variation models: the direct variation model, inverse variation, and joint variation model. The equations for those are here. If we have direct variation, it's y equals k, which is our constant of proportionality, times x. If it's inverse, then y equals the constant of proportionality k being divided by x rather than multiplied. With joint variation, it's very similar to direct variation, except we have more than one variable that is acting on k. With direct variation, the wording would say something like y is directly proportional to x, or y varies directly with x. For example, as the time you spend studying increases, your grade increases. So they move together. If one goes up, the other one goes up. Or as the time you spend studying decreases, your grade decreases. So as one goes down, the other goes down. With inverse variation, the language would say something like y is inversely proportional to x, or y varies inversely with x. And this would be a situation like as the time you spend on Facebook increases, your grade decreases. So they have opposite effects on each other. As the time you spend on Facebook decreases, your grade increases. So they're always moving in the opposite directions. With joint variation, the language would say something like z varies jointly with x and y. So an example of this would be as the time you spend studying and the time you spend in tutoring increases, your grade increases. Or as the time you spend studying and the time you spend in tutoring decreases, your grade decreases. So you can see joint variation is very much like direct variation. It's just that we have more than one thing that's acting on our proportion. Suppose that y is directly proportional to x. We'll use this given information here to find the constant of proportionality k. Then we'll find y when x equals 6. So for the first part, we have, first of all, we know that y is directly proportional to x, so let's make this y equals k times x as our model for direct proportionality. And let's put in this information. Y is 3. We don't know what k is. X is 2. Now we're going to find the constant proportionality k by solving for k. So we'll divide by 2. So k is 3/2. Part B asks us to find y when x equals 6. So our model is y equals 3/2 for our k times x. And if we're finding y when x equals 6, we just need to put a 6 in for our x. When we do that, we see that the 2 cancels 6 3 times, and y equals 9. Suppose that y is inversely proportional to x. Use the given information to find the constant of proportionality k. Then find y when x equals 8. So we'll do the same thing, except we have an inverse proportional model. So it's y equals k divided by x. And the information they've given us here is that y equals 6 and x equals 4. When I try to solve for k here, I need to multiply both sides by 4. So I have k equals 24. That's my part A. If I'm doing part B, they want us to find y when x equals 8. So our model is y equals 24 over x. And if we're finding y when x equals 8, we'll simply replace the x with 8, and we get y equals 3. Now let z vary jointly with x and y. If we have a joint model, then it's z varies jointly with x and y. We'll find the constant proportionality k, so here we have z is 25. We're finding k. X is 1/2. Y is 5. And then we're getting to multiply. On the right side we get 5/2 k. And if I multiply both sides by 2/5, then on the right I have just my k. On the left, 5 will go into 25 5 times, and that 5 times the 2 is 10. So my constant of proportionality k is 10. Now let's find z when x equals 6 and y equals 7. So the model is z equals 10x y. Now we're finding z when x is 6 and y is 7. So z equals 6 times 7 is 42, times 10 is 420. Let's analyze this data. First, we want to determine whether the data represents direct variation, inverse variation, or neither. When we look at this data, x is increasing, and as x is increasing, y is also increasing. Right now we can just suspect that it's probably a direct variation model. So let's assume that for the moment, and we'll come up with our model, y equals k times x. Now let's try and find the constant of proportionality k so we can get our model. Pick any of the xy's out of there, maybe this xy pair. So y is 3, x is 2. We divide both sides by 2, we get k equals 3/2. So we think that our model is y equals 3/2 x. What we have to do is we need to make sure that we test this model with each of the data points in the table. It must fit each of the data points. If there's even one data point where this model does not work, then it's not going to be a direct model. So let's grab the calculator, and we're going to put in, of course, 2 times 3/2. We get a 3. Let's put in the 3. 3 times 3/2 there. And we get 4.5. Let's put 4 into the model. 3/2 times 4. We've got a 6. And let's try with a 5. 5 times 3/2. 7.5. So we did get the correct outcomes every time we use that model. So this is the model, and we know that it's a direct model. And when we graph the equation, you'll see that this is going to be a line. What you can do is to make a scatter plot with your graph if you are familiar with using the graphing calculator, or you can simply just get the first quadrant there and graph the data. So 1, 2, 3, 4, 5, and let's go by 2's this way. 2, 4, 6, and 8. And let's graph, make sure we label this. And we're going to graph 2, 3, 3, 4.5, and 4, 6, 5, 7.5. So when we connect our dots here, then we see it's a straight line. Okay, and if we would graph that, it's also a straight line. We're starting from here, and we go up 3, right 2, and draw the straight line through there. Let's look at this data and decide whether it's direct, inverse, variation, or neither. First of all, we're looking at the data, and the x is going up, and the y is going down. So this can't be a direct model. Remember, with a direct model, when x goes up, y also goes up. The inverse model is when if x goes up, y goes down. So that's what we're looking at here, is probably an inverse model. So remember, our inverse model is y equals k divided by x. And let's pick a point out of there and figure that out. Maybe our first point, 3, 12. So y is 12 equals k over x is 3. If I multiply both sides by 3, I have a k equals 36. So we suspect that the model is y equals 36 over x. But we do need to test it with each data point in the table. So let's see if we allowed x to be 3. 36 divided by 3 is 12. If x was 6, 36 divided by 6 is 6. If we allow x to be 9, 36 divided by 9 is 4. If we allow x to be 12, 36 divided by 12 is 3. So this is our model, and we know that it was an inverse variation model. Let's go ahead and graph this data. Again, let's go by 2's on the y-axis. Indicate that by labeling. And let's go by 2's on the x-axis this time. So we have a 2, 4, 6, 8, 10, 12. When we graph this, you might be surprised at what happens. We have a 3, 12, and we have a 6, 6. So far, so good. We have a 9, 4. So you can see our graph is bending now. It's not going to be a straight line. 12, 3. So when we have an inverse variation model here, then we get a graph somewhat like this. Alright. So any of the direct models, they're going to be straight lines, and the inverse models are going to look like this, where they start high and then they fall off, where when x is getting larger, y is getting smaller. With this data, let's determine whether the data is direct, inverse, or neither. Again, the x data is increasing, the y data is increasing, so this may be a direct model. Let's go ahead and start with that. Y equals k times x, and pick a point to put the data in. We've got a y of 10 here, and an x of 4. If I would divide both sides by 4, then k would equal 5 halves. So we think that the model may be y equals the 5 halves x. So let's go ahead and test this model with each of the data points in the table. I put a 4 in. 4 times 5 halves is going to be 10. I put a 6 in. I get 15. So it already breaks down at the second point. So that means this is not the model, and it's definitely not a direct model. It's definitely not an inverse model. So we'll have to say that this is neither. So we don't have to find the model, and we don't need to graph the equation in the data because it's not one of those models. Let's use the graph here to determine whether the data is direct variation, inverse variation, or neither, and find the constant of variation whenever possible. Right now this looks like it's probably direct variation. As x is increasing, y is increasing. So we get this kind of line of points going like that. So let's say that we have maybe a y equals kx model, and then pick a point out of that, that graph. Let's say we pick the point 2, 4. So y is 4, x is 2, and if we divide both sides by 2 to solve for k, we have k equals 2. So the model might be y equals 2 times x. Let's test it with the data points we have. If x is 1, y is 2. If x is 2, y is 4. If x is 3, y is 6. If x is 4, y is 8. If x is 5, y is 10. So this follows all of those data points up, fits each one of those. So that is the model, and we'll state that it is direct variation. With this graph, let's see if we can figure out if it's one of those models. As x is increasing, then y is increasing. So we could see maybe it is a y equals kx model. Let's pick one of the points. So we have a point 2, 1. So y is 1 and x is 2. When I divide both sides by 2 to solve for k, I get a k value of 1/2. So we think that the model may be y equals a 1/2 x. And we need to check it with each of the points, or at least points that we can see that are on some crosshatch points. So if I put in a 2 here, then 1/2 times 2 is 1. I'll get the correct y out. Let's say here, put in a 4. Half times 4 is 2, and I'm not getting a 2 out for my y. So with just this point, it's the model has broken down. So this is not the model, and it's not an inverse model because as x is increasing, y is increasing. It has to be one increasing and one decreasing. So we would have to say that this is neither. With this data, you can see as x is increasing, y is decreasing. So this may be an inverse model. So y equals k over x, we think may be the model. Let's go ahead and pick a point. Let's say we have this point 2, 4. So y is 4 and x is 2. We multiply both sides by 2. We get a k equals 8. So the model may be y equals 8 over x. Let's go ahead and check the points and see if we can figure out if it's really going to fit everything. If I put in an x value of 1, I do get an 8. If I put in a 2, I will get a 4. If I put in a 3, I would get 8/3, or that would be 2 2/3, and that looks like 2 2/3. If I put in a 4, I would get out a 2. If I put in a 5, I would have 8 over 5, which is 1 3/5, so it looks like 1 3/5. If I put in a 6, I get 8/6 or 4/3, which is 1 1/3. That looks like 1 1/3 right there. If I put in a 7, I get 8/7, which is 1 1/7. If I put in an 8, I get 1, and that is 1. So this does fit, and we know that this is an inverse model. Flow of water. The gallons of water G flowing in 1 minute through a hose with a cross-sectional area A are shown in the table. So we have the square inches opening in the hose and the number of gallons that are coming out with that certain cross-section square inch of the hose. So did the data represent direct or inverse variation? So they've only given us two choices, direct or inverse. Neither is not a choice. So here we have x is increasing and g is increasing. And so we know that it's going to be a direct model. So the explanation is as specifically A here, as A is increasing, then G is increasing. Okay, so as the square inch cross-sectional area increases, then the number of gallons that are flowing out of that hose also increases. We'll find an equation that models the data, and we can graph that equation with the data. Let's go ahead and try and find a model. We know that our basic model is y equals kx. Let's use that with our the variables that we have in this problem. We know that the g equals k times a. Notice that the a is in the x position, g is in the y position. So we'll put g for the y and a for the x. Now let's go ahead and pick one of the points so we can try and find our constant proportionality k. Let's say we pick this point here. I have a 5.4 for my g, and I have a 0.2 for k. If I divide both sides by 0.2, then I get a k of 27. Alright, so I think that the model may be a y equals 27x. So that's our equation that models the data, and then we can go ahead and graph that equation with the data. Let's see, if we have this here, let's go by 2's on the y-axis since we're kind of increasing pretty quick here. Okay, so we have a 2, 4, 6. Let's just do the first few so the reader knows what scale we're using. And on this scale, we're going very slowly up. So let's space that out and let's go by 0.1s. 0.1, 0.2, 0.3, 0.4, 0.5. So if I have, let's see, a 0.2, I ended up with a 5.4, it's about right here. And a 0.3, I get an 8.1, so somewhere around in here. And for 0.4, it said that I have a 10.8, so that'd be 6, 8, 10.8. It's almost 11. So it's about like right there. And for 0.5, 13.5. So let's see, 6, 8, 10, 12, 14. This would be 13. This would be about 13.5. And we were over here at the 0.5. So you can see the line that results here. And if we would graph the y equals 27x equation, we would have that same line. Let's interpret the constant of variation k. So our k, we know, is 27. What does that mean in the context of this problem? It means that as the square inches of the hose increases by an inch, the gallons increases by 27. Okay? Or you could also say as the square inch of the hose increases by 0.1 inch, the gallons increases by 2.7. And you can see that here. As we increase the square inches by 0.1, then the gallons increased by 2.7. Here we have an electrical resistance problem. An electrical resistance of a wire is directly proportional to its length. If a 30-foot long wire has resistance of 3 ohms, find the resistance of an 18-foot long wire. So first of all, in real life, we don't have things running around with variables attached to them. We have to assign those variables to the different properties in a problem. So we have, first of all, electrical resistance of a wire directly proportional to the length. So let's call R our resistance, and let's call our L our length of the wire. Okay, so we have the electrical resistance of a wire is directly proportional to its length. That's our model. And here we have a 30-foot long wire that has a resistance of 3 ohms. So we need to use that information to find our constant of proportionality K. So the 30-foot long wire, that's our L, has a resistance of 3 ohms. Here's our K. And we divide both sides by 30. Then we get K equals 1/10. Alright, so we think that the model is R equals 1/10 L. And we can go ahead and find the resistance of an 18-foot long wire by putting that 18 in for the L. So R is 1/10 times 18. So the R is 1.8. And we know that the resistance, our R, resistance is measured in ohms. So we have 1.8 ohms resistance for an 18-foot long wire. This problem has already assigned variables to the different things that we're comparing here. We have resistance R and current I. So let's read through this again. The current I that flows through an electrical circuit is inversely proportional to the resistance. So that would be a K over the resistance R. Alright, now this is our model. Let's go ahead and put in the numbers they have for us here to find our constant of proportionality K. When the resistance R is 180 ohms, then the current is 0.6 amp. Let's go ahead and multiply both sides by 180. You can grab the calculator and do that. We'll go 180 times 0.6, and I get 108. So K is 108. So we know the model is I equals 108 over R. Now find the current when the resistance is 54 ohms. So we have I equals 108 over the resistance, which is 54. When we simplify that, we get an I of 2. And remember, I was measured in amps, so we have 2 amps. That covers that section. Go ahead and try the homework. And be sure and let me know if you have any questions.